Hello, Flat Earth researchers, debaters and debunkers. I'm down at Bangtao Beach on the west coast of Phuket to show you that the calculations for the distance to the horizon are pretty much correct. The mathematics, of course, uses geometry, but we're going to see from this that it's not the geometry of being on a spherical Earth that creates the horizon, as we are commonly led to believe by mainstream education and the so-called science behind the mathematical descriptions of observations. It is simply the geometry of perspective. So we can see here this headland out that we are pointing at here is less than 3 kilometers away, and over the other side of this bay we also have another headland. We'll measure the distance on Google Earth and we'll have a look at that, and we'll see that according to the mathematics for the distance to the horizon, we have a horizon that is pretty much in line with these two headland points, and we can see that the horizon starts at around that point, or appears to be around that point, and this is probably something in the region of where it should be given my elevation, which is just under 2 meters, I'd say, standing looking across this flat water. But of course it is commonly believed that the horizon is where water starts to curve down and away from us on this alleged globe that we live on. But we'll see that really all that is just the extent we can see across flatness. So bearing in mind that we have a horizon that appears just a little bit beyond that headland there, and about the distance of that headland there, and according to the mathematics for the horizon, that should be about right. But then what we have is boats and ships and what have you in the distance that are much, much further away than this 2 to 3 kilometers of the headland you can see out there. So they haven't sunken down below any curvature. They are just they just appear to be on the horizon, simply because once objects reach the horizon, they will sit on the horizon until they're just too far away to see. I'm gonna see if I can pinpoint. There we go, there's something else on the horizon there. Hopefully you can see that. All right, that's miles away. And of course it's much further away than the two headland points either side of me, on my right and on my left, where the horizon appears to be. So this is simple observational proof that when things reach the horizon, they just carry on off into the distance. They don't suddenly disappear. There's another one. Let's see if we can zoom in on that. Okay. There are ships and what have you out there, which are way beyond the 3 meter limit of the horizon. So basically here what I'm saying is that there is no contest that the horizon will appear to be between myself here on the beach and up to there is about 2.5, 3 kilometers, which kind of fits with the mathematics for a horizon. Okay, but this is because, look at all this water between myself and the horizon. So yes, at this low level, it appears that we can only see, 2 to 3 kilometers to the horizon. But of course, anything that's on the horizon, we can also see that beyond, way beyond. They could be 5, 6, 7, 8 miles away. They could be 10 miles away. And of course, at some point, those ships will become too small to be able to make out at all. So what I'm going to not show you in another illustration right now is what we need to consider when we see the sun setting, which could be several thousand miles away in the distance, and of course it appears to be cut off by the horizon. But we've got to remember what else is between us and however far away that point is where the sun appears to be setting several thousand miles away. So we'll have a look at that. So here's Bangtao Beach on Google Earth, and between the point that I was stood on the beach marked here and the headland that we saw in the footage just now on the left, the distance is 2.22 kilometers, or if we do that in miles, that's 1.38 miles. And remember that the horizon appeared to be somewhere beyond this headland. Now let's do it for the other point that we saw on the right there. So I'll go from there on the beach to this piece of the headland, which is now 3.33 miles or thereabouts. Okay, if we do that in kilometers, it's 5.36 kilometers. And remember, at this point in the footage, when I was standing around 2 meters in height above sea level, then the horizon appeared to be at the same level as this piece of headland here, where it was just a bit beyond the closer headland here. So, you know, that gives us an equivalent to what is the standard, and we can have a look at that now. Here on this distance to the horizon calculator, which is based on the observer's height, if we put in an observation height of 2 meters, we get a distance to the horizon of 5.1 kilometers. So if we go back to Google Earth, this point was 5.36 kilometers away from where we were looking, and the horizon was there. So that would appear to tally with the mathematics that is used. So let's just have a look at the mathematics that they are using here and see what we can make of it. So here we have a geometric model or illustration showing us how the calculations are made. What we have here is essentially a triangle that's been created by the observer O here, looking down towards the horizon here, that creates a right angle going down to the assumed center of the assumed spherical Earth and then back up. So that gives us this right angled triangle to make our calculations, and it will be very accurate in of the model itself. There is no disputing the geometry here and how you can make very predictable calculations once you know the height and the angles, and you have assumed the circle of the Earth is a certain radius. So let's have a look at what it actually says. This calculation should be taken as a guide only, as it assumes the Earth is a perfect ball, 6 million meters radius. It also assumes the horizon you are looking at is at sea level. A triangle is formed with the center of the Earth C as one point. The horizon point H is a right angle, and the observer O the third corner. Using Pythagoras' theorem, we can calculate the distance from the observer to the horizon, OH, knowing CH is the Earth's radius, and CO is the Earth's radius, plus observer's height, V, above sea level. Okay, so again, there is no disputing the calculations that you can make once you have assumed a model. But does this fit with reality? Well, I'm saying that the geometry does fit with what we see in terms of looking across to the horizon. But this idea that the more height we gain above the horizon, the further down we have to angle down our line of sight is, of course, a big bone of contention. Anyone who looks with any discernment, even in an aircraft, will see that the horizon is in fact dead ahead. So that this then changes everything when it comes to making observations and then calculating the distances that we should see. And of course, in reality, as I just showed you, we see things way beyond the horizon that should be hidden by this alleged curvature. So while we're at it, we can also make another calculation and see if the model we've been given for a globe Earth fits with the reality of observations we make in real life on the actual Earth. So here what I've done is just simply measure the distance between these 2 points either side of the cove here, and we have a distance of 4.46 kilometers. So why am I doing this? Well, it's simply because we all know that the horizon is said to be where curvature begins, and anything beyond the horizon is apparently supposed to curve down and away from us, given the mathematical model for a spherical Earth. So naturally, it's supposed to be a sphere, so that means that there should be curvature in all directions. So any claim that there is curvature in front of us, at or beyond the horizon, should also be the equivalent on another horizontal line of sight. So here we've got this 5.46 kilometer distance across our own horizon that we could see within the bay here, and if we go to this Earth curvature calculator and put in the distance of 5.46 kilometers, well, the amount of curvature that we should see across that horizon equates to 2.34 meters. And as you can see from the footage, that's just not something that we observe across this 5.46 kilometer horizon, is it? So this doesn't fit with reality. It might well fit with a model and be very accurate for that model, based on the geometry that is used and the assumptions that are made when making a two-dimensional illustration and using Pythagorean theorem or Pythagoras theorem. So again, in of the model itself, it will be perfect and you'll get some very accurate results from any calculations that are on it. But we do not see in reality 2.34 meters of curvature on a 5 kilometer wide horizon, and it doesn't matter how wide that horizon is, you'll never see curvature. So then of course we get told there's another explanation. It just looks flat, it's locally flat. Unfortunately, that tells us that we just have to have faith in a model rather than looking at the reality and seeing it for what it really is. So we've already seen with real life observations that we can see ships on the surface of the water much further away than they should be on the model. They are on the horizon as they go off into the distance, telling us that the surface is indeed flat, and we are not seeing any evidence of curvature going down and away from us in front of us, because we see ships on top of the horizon, not going below it, and we see no curvature horizontally either anywhere we look, and that is despite the model that we are given, like this one here, of a spherical Earth. So again, the model can work fine in of itself, and when you map things out on a sphere, then it's a projection that works for all intents and purposes. Nothing really changes except that we can see further in reality than we would be led to believe given the mathematical model. But now I've zoomed out of Phuket, and so we can see the other land masses around us, because I want to look at sunsets. And of course it's common consensus that the bottom of the sun gets cut off as it goes down towards the horizon, not because the sun's moving away from us, but because the spherical surface of the Earth in front of us is blocking the sun off as we roll backwards on this assumed model sphere. Of course, nothing in our reality tells us or can in any way be really truly measured to demonstrate this notion. All we have are illustrations. So let's have a look at where the sun should actually be when we watch it set across the Andaman Sea when we're on the west coast of Phuket. So if we look at timeanddate.com and we look at this calculator for sunrises and sunsets off Phuket, the video was taken on the 17th, and we can see here that the sun sets at 18:28, 6:28 in the evening. So let's just go and have a look at this day and night map, and we can see at that time, 18:28 on the 17th of January from Phuket, the sun is directly above this point near South Africa. So it's quite a few thousand miles away from us, and we have a lot of sea and land between us. Let's just go and see how far that actually is, and we'll use the ruler again to go from Phuket. We have to go beyond Sri Lanka. Let's just try and turn the Earth. Oh, there we go. And oh, we've somehow ended up going all the way down here to Africa. 9,000, almost 10,000 kilometers. All right, 9,886 kilometers. So the sun is said to be directly above this point of Africa when we see it setting off Phuket. Yeah. If we zoom out even further from this model of a spherical Earth, we'll see again that this 9,800 or so kilometer distance to where the sun is above South Africa isn't what we see in reality when we see the sun set off Phuket. Yes, the sun does set at the time that we saw on timeanddate.com, but we can see from this diagram that it's here around the bottom of India where the sun should get cut off by this curvature of the Earth that would in effect be bulging up in front of us. That's of course not what we see. We see flatness. So that just doesn't fit with reality either. But let's look at how sunsets can and do work in reality. Let's just briefly go back to this flat map projection of where the sun is when it's setting for us, when we're looking off the west coast of Phuket, and stress that there is no dispute of the accuracy of the model, the that we see projected in various ways. The model is the predictability of the sunrises and sunsets in any given location at the particular times that they occur, or the path of the sun and the moon. There is no disputing when and where we see these things occur, but we can see that it can be projected or illustrated in all manner of ways. So there isn't one that takes precedence over the other. The model is simply the predictability of the sunrises and sunsets, simply because people have been keeping records for thousands of years without any consideration as to the actual shape of the Earth. It doesn't matter. You can assume the sun and the moon are moving and the Earth is flat, or the Earth is moving or rotating. However you wish to do this, you can create an illustration based on the fundamental model derived from the sunrise times and the sunset times and the angles to the sun from any given location. Again, nothing changes in what we observe when it comes to seeing the sunrise and set and watching it go overhead or make an arc across the horizon. It is all observable phenomenon, and it's quite accurate. But what we have to keep in mind is that what we have here between Phuket and the sun above southern Africa is, of course, a huge land mass here, comprising several countries, which is probably several hundred miles or a few thousand miles across. We have lots of ocean, and we possibly have the Nicobar Islands as well. But in reality, would we ever see this far? Can we see hundreds or thousands of miles, even across a flat surface? Would we expect to be able to see the southern part of Africa, or even the Nicobar Islands from our place on the beach in Phuket? Of course not. Even the ships, by the time they're a few more miles away, are almost becoming swallowed up in the horizon, or just too small to see. The light from them isn't reaching us, that's being reflected off of them. So we cannot ever realistically expect to see land masses that are any distance between us. But we do have to consider what we would see if we were near those land masses, and this will help understand how the sun can appear to set above a flat Earth but never actually does. It just carries on going off into the distance, and yes, it will get cut off at the horizon, but that's not because we're on a spherical Earth and rolling backwards away from the sun. When we talk about flat Earth, it's with the understanding that the Earth isn't really flat. We're talking about a level Earth with lots of terrain on it, and it not being a sphere. So, of course, in the real world, in the natural world, there is no such thing as absolute flatness, whether it's water or land. Nothing is flat forever. It's going to be rugged. And as we see here, we've got a photograph taken of what could be a sunrise or a sunset that's being cut off by the hill in front of the photographer. It could be a mountain. It's a little bit difficult to tell. The point is that on a local level, this is what's happening. And we know from experience, and is demonstrable, that when something is higher than us, i.e. the sun, and it goes off into the distance, it will appear to sink down towards the horizon. That's simply a fact of life, a fact of any kind of observation. This is the geometry of perspective at play in our vision. It gives us that depth, and of course it can be converted into triangles, and using the Pythagoras theorem and geometry, we get the same results as we do for the geometric spherical Earth. Perspective is the imaginary curve, and the reality is that the sun gets cut off by all the things that are present in front of us, even if we can't see them, because we know that on a local level this hill is blocking off the sun. But if we got further and further away from this location, if we backed away, then of course we would see more and more land. This would all become smaller and it would become more level and flat. It would make up our horizon, and the further away we got, we would see that the sun was cut off, but with a much more level line, because eventually we get far enough away that we cannot see the land. We cannot see the shape of the land or anything else that's cutting off the sun. Let's use a couple of very simple diagrams to illustrate the point here, so we can see how the geometry of perspective, rather than the geometry of an imaginary spherical Earth, can be used to describe how a sun appears to sink down towards the horizon as it travels away from us on a level stationary Earth. So this is a side-on view that I've put together of what could be the Nicobar Islands, or even the landmass of South Africa, up to 10,000 kilometers away from Phuket. So we have Phuket off to the east there. It really doesn't matter how far the distance is, it's arbitrary, but the point is that what we have happening here is the sun moving in the sky, maintaining a consistent height above the surface of the level Earth, and going off to the west here. So at this point is where we saw on the time and date map that the sun is above South Africa, and it's setting, or appearing to set, for the observer in Phuket at 6:30 local time. So what's happened by now with the sun over here is, as we saw in the previous image, we have the sun will be cut off by not only the land beneath it, but also the clouds above that land, or simply just the increasingly dense atmosphere that we get, or the air that is very dense near the surface, that also is really works in much the same as water. There's a limit to the distance we can see through the clearest water. So with air we can assume the same thing happens, but over a greater distance, because obviously water is much denser than air, but over distance we get the same effect. The air becomes so thick and soupy that you really can't see through it. So eventually the sun will get cut off by the land or the clouds or the dense air that's in that layer just above the surface, and everything beyond the sun here will of course now be in shade. This sun will be casting a shadow across these clouds, and of course the further away it gets, the longer those shadows will be, and for us in Phuket we will then be in darkness as the sun travels off to the west and doesn't go down below any horizon. The horizon is everything that's on the surface and above the surface that blocks our view of the sun and will in fact cut it off. As I said earlier, nothing changes in terms of what we see when we look at the sun in the sky at any given location or at any particular time on the Earth. There is no change there. But what we can do is illustrate the mathematics of what's happening in the eyes of the observer, rather than assuming that we're on a spherical Earth to make sunsets happen. So I've tried to do this with this side-on illustration here of the perspective that governs any and all observations that are made. In fact, if you're going to make an observation, you must consider how our eyes work. And so here, just as we had triangles in the Pythagoras theorem to illustrate how an observer must have a downward angled line of sight towards the curved surface of the Earth. We can also use triangles here to illustrate how the sun can appear to set, even though it doesn't actually do so above a flat surface. So it might appear quite simple, but I'll just take you through it to make sure we're on the same page, as it were. So here we have the observer standing on the beach, as we were in Phuket, and we have a flat surface here, and we have a sun above us at midday. So the idea is that the sun continues on this actual path. So this is the actual path of the sun as it heads off into the distance. So let's say that it's at this point 6:30 in the evening for us on the beach in Phuket, and the sun is now above South Africa, as we saw earlier. But what in the eyes of the observer, the sun will have taken this apparent path downwards. As we all know, anything above an observer that goes off into the distance will appear to sink down towards the horizon, which will be the observer's eye level if and when they are looking straight ahead. And here we have a flat surface, but because we were just of an elevation of only 2 meters on the beach in Phuket, then what we have here is the surface appearing to rise up in front of us to our eye level at only a short distance. So again, the mathematics for this is fine. This height of the observer is arbitrary. We still end up getting triangles. We can take this line all the way to the horizon if we like, but I'm illustrating it this way to show that we have a surface that rises up to this point that's possibly only about, appears to be about 3 to 5 kilometers in front of the observer because of the observer's height above the surface. But the sun is much, much higher in the sky, so it takes a much longer path, and there's a much slighter decline as it goes off into the distance and eventually reaches the observer's horizon. So that's why we've got this short line here representing the short distance across the surface to the horizon. But then after that, anything that's still on the surface will simply appear to be just here above or on the horizon, and it will still be off into the distance and we'll still be able to see it. It doesn't go down any curve as long as that object is big enough and it's not obscured by the other conditions such as dense air or mist or clouds or what have you. So that's really what's happening in the eyes of the observer, and this is how we can illustrate that happening in a way that fits with reality. And this, of course, doesn't make any assumptions about what the sun is. What I'm showing you here is how it can be illustrated in a very similar mathematical way as we have the illustrations for an observer above a spherical Earth, simply because when we use triangles we end up with 180 degrees in a triangle. So of course that represents a semicircle, and of course you join these together you get 360 degrees. So you end up blending geometry and trigonometry with the same angles and ratios that we get when we are talking about illustrating what an observer sees above a spherical Earth. But in this case, whatever is on the surface or above the surface in the distance, be it the land or clouds or simply the dense air in the distance, that's what cuts off the sun as it goes off and appears to set, when really it doesn't have to do that above a level Earth when you have a local sun. Again, I'm making no assumptions as to what the sun is and how it all works. This is simply to try to help you break free from the misconception that the only reason we see the sun sets is because of this belief that we live on the outside of a spinning spherical Earth, and that we must have faith that beyond the horizon is curvature that we never ever see, and has been evidenced just now to not exist when we see boats beyond the horizon going off into the distance much further than we should be able to see given the mathematics for the globe. So I would say that this illustration of perspective is a much more realistic and pragmatic or practical diagram of what's going on in the eyes of the observer, rather than assuming the physically impossible notion of us being on the outside of a spinning ball. Thank you very much.